Yes, I'm very happy to introduce our second speaker, who's Michael Hartisch. So he moved this week, as I understood, to University of Passau as a postdoc. Before he was a temporary professor in Erlangen, Nuremberg, and in Siegen. And his research is focused on optimization under uncertainty and also a very new and exciting topic on explainability and interpretability, but not for the machine learning world, but for the optimization world. And also, I have to mention he recently published a book together with Mark Gurrick. So if you're interested in robust optimization for combinatorial optimization, I can very much recommend this book. And thanks, Michael, for being here. The floor is yours.
Yes, thanks for the introduction. Thanks for having me. Yeah, as you mentioned, well, officially, I'm now a member of the University of Passau, but this is just as of October 1st, so the layout is still in the FAU style, but I guess that's fine. So what I'm going to present is a joint work and ongoing work with Mark Görig and Sebastian Merten on robust interpretable surrogates for optimization. So as Janis already pointed out, well, we are trying to do interpretability also in optimization. So why do we need to do this? Well, we would argue that stakeholders need to be able to understand the solution process. And by stakeholder, we mean, well, anyone who is influenced by the decision. And this could be the worker. This could be the decision maker itself. This could be some manager. Okay. And the reason why there is this need is that, well, complex models can result in reluctance to use them, even though if they have shown to be beneficial. And there's actually another reason, which is, well, there is a law that tells us that AI systems need to be transparent. So this is the AI Act from the EU. So since we're talking about interpretability today, we should get in line and figure out what this is supposed to mean. So interpretability means that there should be an easily comprehensible rule available, which can be used to map instances to solutions. And so this process needs to be easily comprehensible. So that means we kind of are able to give out instructions or manual on how to move from instance to solution, and this way kind of disclose our internal logic. And in particular, this mechanism is not a black box. And if we believe Cynthia Rudin, this is what we should strive for in machine learning. And I think this translates also to optimization. This definition has some kind of a flaw because it uses this term easily comprehensible, which is quite a subjective term, right? So I assume we all can or could agree that LP solving using the simplex method can be viewed as interpretable, right? Because we can take a look at the instance, we know what's going on there, we understand how the simplex mechanism works, and after we obtain the solution, we know what this actually means. But is it really comprehensible for everyone? So if the worker comes along and asks you why this solution was selected for this instance, I'm not too sure whether this worker is going to be happy if we just provide the pseudocode of simplex. So it very much depends on the domain knowledge, what is comprehensible. Okay, but we still want to do something that is comprehensible. So what do we do? Well, we just go along the lines of the machine learning community that tell us, well, okay, linear models and decision trees are examples for models that are interpretable. But still, in both cases, sparsity is quite important, right? Because you could also have a decision tree with huge depth and difficult to understand splits. So still, they need to be somewhat sparse. Okay, and this is what we will focus on decision trees. Okay, and quickly, let's take a look at what is out there on interpretability and optimization, and there's actually not that much out there. So there are works on interpretable policies for optimal stopping. There are MIP formulations for tree-based models for clustering. But those two still are, I would argue, quite close to machine learning, because what they in the end do is they classify input, and we don't want to have a class label on the leaves, but a solution to the optimization problem. There are other research areas that try to that are related to, or that there's solution learning, where they try to learn the mapping from instances to solutions, which is kind of what I just argued what we need, but they usually don't focus on comprehensibility here. And another area is the generation hyperheuristics, where there also are works where they try to find heuristics of limited size. So again, sparsity is something they wanted to ensure. And then there is the work by Mark Jurek and me from last year, where we proposed a framework that allows us to find interpretable optimization rules. So for example, those decision trees with fixed depth that mimic this optimization process. And I will use this term optimization rule and the term surrogate kind of interchangeably. Okay, so let's take a look at another example on how to view interpretability in optimization. So let's take a look at this shortest path setting. So we are in Chicago and we want to move from the northwest to the southeast of the city. And what we would do in standard optimization, we would just wait until the scenario is revealed, and depending on the costs of the or the travel times of these edges, if the costs are like this, we will take the red solution. If they are blue, we'll take this solution. And so for every new parameter setting, we will have a new solution. And if you believe my argument from before, this is not interpretable because the mapping from instance to solution is not comprehensible. Another approach, which most of you might be familiar with, is a k-adaptability, where the idea is, well, let's just select k solutions, so in this case, 4 solutions. And we can, of course, optimize which might be the best solutions to take. And after a scenario is revealed, we assign one of these solutions. So if this scenario is revealed, we'll take the best of those k solutions, and in this case, it's going to be the green one. But it's again missing the easily comprehensible mapping from, well, this scenario has to be green, right? So there's no easy mapping. Why should this one be green and why should this one be brown or orange, right? So this is also not interpretable. And then there's our approach where we want to have this easily comprehensible mapping, right? So that means, well, if we just draw those two separating lines, we can find an area where all those points are green and all those points are orange or brown. And this actually translates to this decision tree, which I would say is obviously easily comprehensible because it just queries single cost entries at every split, and in the end assigns a solution to an instance, right? So you put in a new instance, which is moved through the tree, and then we just have the solution. And this is our interpretable surrogate. So that means this original framework for finding interpretable surrogates tries to find this mapping that maps cost scenarios to solutions. And it does it by taking a set of candidate scenarios. So the candidate scenarios you can think of as the set of points here. And the goal is to find this surrogate, to find this decision tree that maps the scenarios to the solutions with respect to some decision criteria. So that means this surrogate should be optimal with respect to the average case, for example. Okay, and this is actually the case that we will consider here as well. Okay, but we actually want to talk about robust interpretable surrogates. So how does this come into play now? Well, the idea is that these cost scenarios that are the input for this optimization rule for this surrogate, they need to be observed, of course, but they might be disturbed. Okay, so we might have observations that are different from the true realization, right? So let's say, of course, we can go to Google Maps and check the estimated travel time of one road segment, but this does not mean that this is actually the true travel time, right? And if we now apply our surrogate using these disturbed observations, this obviously might yield to bad solutions. Okay, and hence the task is to find a surrogate that is robust with respect to these disturbed observations. Okay, let's go back to our shortest path example. So a very small example. We want to move from S to T. So we basically just have two options: the blue solution or the red solution, and we have a set of candidate scenarios. So again, the task is to find a surrogate, a decision tree for finding paths from S to T. And this decision tree should be best with respect to the minimum sum of all candidate scenarios. So again, the average criteria. Of course, it has to be comprehensible, as I outlined before. But now there's some uncertainty. That means the observations of these scenarios might be disturbed by at most 5 units. We'll see this in the example now. So the nominal solution actually will not use the def2, which would be allowed. It just uses a def1 decision tree, just queries the first entry. So only those entries are queried. And it is kind of obvious that this makes sense. So we just check whether this is a small value. If it's a small value, we should take the route using C1, C2, so the red path. And if this value is large, well, let's just take the solution that uses C3 and C4. Okay, so far so good. But now the disturbance might come into play. And let's say in scenario 5, we don't observe a 10, which is the true value, but we observe a 5. And if we observe a 5 here instead of the 10, what will happen? Then this instance will get into this optimization rule, and it will yield the red solution, right? So instead of only paying those 4 units, we have to pay those 18 units. So that means the cost is much higher than anticipated. So maybe there are better decision rules, better optimization rules here for this instance. And indeed, there is one. So what we can see here, well, we now use a def2 tree, and we can see in this picture that this worst case from before is no longer a worst case that is allowed to happen, right? Because we cannot move this scenario 5 to the red area anymore. And in fact, the worst case actually will be that scenario 2, which is this one, will now be moved to the blue area, right? So we now query the first edge, the second edge, and if the second query is a 6.5 rather than 6.5 rather than just the 5, it will be also mapped to a blue solution. But in the end, what we lose is not that much, right? Before the value was 50, and now this robust value is just a 41. Okay, so let's make this a bit more formal. So what we also always have is some kind of optimization domain. So in the examples, we've just seen a shortest path, but it could be knapsack, it could be scheduling, it could be anything. And we have a set of optimization rules, so a set of possible surrogates that we want to consider. So in here, we have all those decision trees of def4 with those easy splits. And as an input to our framework, we have a set of capital N cost scenarios. And we know that these cost scenarios might be disturbed when we actually observe them by some psi, which might move this value up or down. So the robust problem then becomes, can we find a surrogate, such a decision tree, such that for any disturbed observation, we are still good on average? And what we see back here is that this optimization rule, the surrogate that we obtain, takes as input these disturbed observations, will overall yield a solution, but what we have to pay is the actual true underlying cost and no longer the disturbed observations. So what did we consider for the uncertainty set? So we did consider 2 different types of budgeted uncertainty sets. So the first case is, well, we have a global budget, and the adversary can use this global this budget on all scenarios, however he likes to do. And we have a local budget where we have a local gamma for every scenario, where in this case the adversary can use this budget just for every single scenario. Okay, so how can we tackle this problem? Well, we implemented a scenario generation approach where the master problem has the task of finding a decision tree, which is just based on a subset of the uncertainty set. We can model this via an MIP formulation. And here we actually use a flow-based formulation for trees. Again, trees have to have fixed depth, and we only query single cost entries at every split. And what we also did is, well, we just pre-computed all the potential splits. So taking the candidate scenarios, we just take a look at every entry and figure out what could be a possible split. So the split is actually not a continuous variable, but just a combinatorial problem, just a binary. Okay, so after we have solved this master problem, we've obtained a tree, and then we put this tree into the adversary problem, where the task is now, for this given tree, find the worst case scenario. And what we do here is that we can again pre-compute the adversary cost. So we can pre-compute how much budget or how much of your budget do you need to spend to misguide a specific scenario into one specific leaf. So that, again, just yields a lot of binary variables. So again, we are in a combinatorial setting where the question is, which scenarios does the adversary want to map to which solution while still maintaining the budget? Okay, so we did not really expect this scenario generation approach to scale that well. So we also came up with some heuristics. So the first one is that we can just guess solutions and then find a structure of the decision tree that works best with these solutions. And we can, of course, repeat this, guess new solutions, and find new optimal trees for this set of solutions. The second approach is, well, we can also just fix the tree. So we can fix the structure of the tree. We can fix the splits of this tree, and then optimize the solutions that appear at these leaves. And what we were able to show for the second part is, well, this is still an NPR problem we need to solve even for the selection problem. And also the first heuristic is NPR, just using some kind of historic results. And as a third heuristic, we kind of combined these two approaches, where in the first step, well, let's just guess a solution, use our approach to find a tree, then fix this tree, use heuristic 2, and find the solutions that work best in this tree, take out these solutions, move them again back to heuristic 1, and so on. Okay, so this is kind of an alternating approach of heuristic 1 and heuristic 2. Okay, so we did some experiments on, again, the shortest path problem, a quite small problem, just a 4x4 grid graph, where we want to move from the southwest to the northeast. This capital N, the number of candidate scenarios, was 3, 5, or 10. And when we created those candidate scenarios, they were all based on 3 random scenarios, just so that these candidate scenarios are somewhat connected, right? Because otherwise it would just be learning something on a lot of noise, right? For the budgets, again, it might be somewhat arbitrary how we selected it, but the idea was, so in every scenario we can change the edge cost on average by 1/5, and for the local budget, every scenario can be changed by 1/10. Okay. So we set the time limit to 1 hour and had 20 runs for each constellation, and then we obtained those surrogates, and we now compare them back to the nominal optimal surrogate we can find using our old framework, and we compare them using some measures. The first one is, well, let's take our candidate scenarios and take a look what happens when we disturb them. What happens if we just take in the candidate scenarios that are not disturbed, and what happens if we generate further scenarios using our old approach of generating scenarios, and maybe we also perform good here. So let's take a look at the results. So in the top table, we have the results for the global budget, here for the local budget, and we take a look at performance on those disturbed values. So what we would expect is that the nominal solution performs worse than our approach, which is indeed the case, right? So minus is that we get better, which is no surprise, right? Because all those approaches actually hedge against this kind of uncertainty. And we can see for the local budget, we are actually able to have a bit better performance compared to the global budget. What we also can kind of see is that our scenario generation approach, as I said before, does not really scale that well. So actually, it does not find the optimal tree within the pre-prescribed 1 hour. But what we can see on the right-hand side is that in particular, this alternating approach that uses heuristic 1 and 2 in an alternating fashion does perform rather good. When we take a look at the nominal performance, here we would expect that the nominal solution performs best, which again is true. So we don't find any negative values over here. So what we can see is that the incumbent of the scenario generation approach is quite good compared to the nominal, but I would say that's not really much of a nice result because it's just an incumbent of this approach. But when we take a look at the heuristics which did perform quite good on the disturbed observations, we see, well, we do not lose as much as we gain in comparison to the disturbed setting. Okay, and finally, what did we compare against? Yeah, we did compare against other scenarios we generated that are not those candidate scenarios. Again, the incumbent solution of the scenario generation approach does perform surprisingly good. So it seems to generalize quite nice. But also for the heuristics in both the local budget and the global budget case, it looks like we do quite well even on out of sample scenarios. All right, so to conclude, I tried to motivate you that we should acknowledge that there is a need for interpretability also in optimization. And we now made first steps towards robust interpretable surrogates. And we did this by extending the approach we already had to hedge against uncertain observations that will be used to feed the surrogate. And the experimental results were kind of promising, right? So we have seen that we have a large gain in performance on the disturbed observations. We have a rather small loss in the nominal performance. And there might be even a chance that we are quite good on out-of-sample scenarios. We've also seen that the optimal scenario generation approach is quite slow. But on the other hand, our heuristics did perform quite well. So as a note, those are very fresh results. So it's still work in progress. So they're still under scrutiny. So there's likely a lot more to do and a lot more to take care of. So for example, of course, more experiments, right? So larger graphs, maybe even real world instances. So we have this Chicago graph, which we like to use. So let's put this robust framework on this. We also need to take a close examination on the effect of the budget size, which we have not done yet, right? So we just have kind of fixed these gamma values, and we're just taking a look at the results. But we should be careful here. What also would be nice, not only take care of the shortest path setting, but also take a look at knapsack or any other optimization domain, just to make sure that this also works fine there. And maybe a more long-term goal might be, well, let's just also take a look at other robustness concepts that might fit into this interpretable setting. So in this talk, I showed that we hedged against disturbances of these observations, but maybe we can also hedge against misuse of the user. So we might be able to come up with something. How does a user use this decision tree, and what kind of mistakes could a user make? Okay, so that's it for my talk. But as a final note, and as Jan has already mentioned, there is something that might be highly relevant to this community. So I want to announce that Mark, Georg, and I have recently published this book on robust combinatorial optimization. This book is meant to serve as an introduction to this topic, so it can be used as a guide for your lecture, or it can be a nice starting point for a researcher interested in this topic. So here, feel free to reach out to us if you're interested. So thanks again for the organizers for having me, and now I'm happy to take questions.